Hello, everybody. Chris Neidl here from the OpenAir Collective and Rethinking Removals. We're very pleased to rebroadcast today for our global audience the Carbon Removal Challenge Finalist Showcase, which was held on Tuesday here in New York City as part of Carbon Unbound, which is the premier convention or gathering of folks from all over the place that are involved in carbon removal. So it was an amazing audience, an amazing exposure for these 5 amazing teams from all over the world. So what we're going to do is go ahead and play the recording of that. But the bonus is that representatives from each of the 5 teams are actually here on the chat. And so if you have questions about their presentations, you're going to see 5 8-minute presentations from each team. And if you have any questions about it, you can go ahead and answer it, and folks will be able to chat your reply directly. And with that, I'm going to go ahead and start the show. Okay, folks, we are going to start. Welcome to the 2nd annual Carbon Removal Challenge. Let's make a little bit of noise for this achievement. Great. Tonight's event is the project of OpenAir with an enormous amount of help and amazing partners in Carbon Unbound. And my name is Chris Neidl. I'll be your MC tonight. Really excited to be here because I've really seen it evolve from a little tiny idea that Matt Parker, who we'll meet in a minute, came up with a few years ago, and to watch it evolve into this just incredibly interesting project. Wait until you hear from the actual projects and what these students have come up with. So what we'll do right now is I'm going to welcome Matt Parker, who's really the driving force behind this project, and he's going to tell you a little bit about the amazing sponsors who we've teamed up with this year to help make this project happen, and then we'll move forward with the presentations. Matt.
Reminds me a little bit of my stand-up days. How's everybody doing? Don't forget to tip your waiters. Hi, everybody. I'm Matt Parker. Thank you so much for coming to the Carbon Removal Challenge. We're going to put up the slide deck for thanking our sponsors. In just one. That's the one. There we go. This is a joint venture from a lot of people who worked really hard to make this happen. We want to begin by thanking our sponsors, who really, this would not be possible without them. We're going to start with our, we do some carbon removal puns for our sponsors. So we're going to start with our Gigaton sponsors. First of all, Peter and Erica Reinhardt, who provided the vast majority of the funding to get the teams here to present to you today. So let's give a nice round of applause to Peter and Erica Reinhardt, our presenting sponsors for the 2024 Carbon Removal Challenge. It really is a massive debt that we owe to them to making tonight happen. And not just tonight, the entire venture getting to this point. We also want to thank our venue sponsors, Carbon Unbound. They gave us this venue, and they have provided us with a unique opportunity for the teams to actually attend this conference and be able to rub elbows with some of the leaders in the carbon removal space and really create opportunities for them. A big part of what we want to happen with the Carbon Removal Challenge is for these teams to get a foothold in the carbon removal industry and become the workforce of tomorrow for carbon removal, create that human capital. We really modeled this after solar car races that started in the early 1990s that we think were partially responsible for that exponential rise we've seen in solar technology. We want the same thing to happen for carbon removal. So thank you to our Gigaton sponsors, Peter and Erica Reinhardt and Carbon Unbound. We also want to thank our Megatons level sponsors, XPRIZE, Activate, NYU, Tisch, NYU Alliance for Public Interest Technology, Carbon Upcycling, who you'll hear about from a second, who made these very cool medallions that are our prizes for the Carbon Removal Challenge, and Mitsubishi Corporation. They have all provided us with important sponsorship and support for this challenge. I don't have the clicker. Where's the clicker? Next slide? Yeah. Round of applause for our sponsors. We also have a number of really helpful partners who help publicize the challenge, get it out there to different teams around the world. This really is a global challenge, and we wouldn't have been there without OSHWA, the DAC Coalition, Studio Possible, Possible Studio, I always get that backwards. Carbon to Value Initiative, Climate Draft, the MCJ Collective, and Green Portfolio. Thank you for helping us spread the word and getting these teams here and getting the people here to support them. And then finally, but maybe most importantly, except for the sponsors are always most important, but behind them are the judges who help make this happen. There's bios on the sites for these people. I can't go through all these names right now. We don't have the time for them. But they judge these projects and determined what the 5 finalists would be for this challenge. And then our organizing team, which have worked tirelessly over the course of this year to make this challenge happen. Please give a round of applause for our judges and organizers. It's a really great initiative. So now I'm going to bring up, where's Ali? Ali is, yes, sorry, thank you. From our venue sponsors, Carbon Unbound, the CEO and President? Just CEO? Just CEO? Okay. Oliver Katz of Carbon Unbound.
I'll just keep it very short and sweet because it's definitely not about me. But yeah, we're really happy and excited to be hosting this challenge at Carbon Unbound. You guys are the future of the industry, so we're really excited to see what you're building, and also just to Matt and the team just building this incredible challenge. We support it wholeheartedly, and it's really important just to push innovation forward in such a pressing industry. So yeah, congratulations to everyone. Hope you have a lovely time this evening, and look forward to spending some time with you over the next sort of hour or so. Thank you.
And then just one more sponsor we're going to hear from tonight, Carbon Upcycling. This is, I mentioned these very cool awards. Madison's going to come up here to talk about these 3, well, I don't want to steal your thunder. Hold on, I'll let you talk. Yeah.
I just interrupted mid-speech there. Sorry. Yeah, we're really, really excited to be a part of this, small part of this award. Carbon Upcycling is a carbon capture and utilization company. We're based in Calgary, Canada. And essentially what we've done is we've taken CO2 emissions from a natural gas plant, and we've actually stored it in this plastic here. So this award is 7% captured CO2. And yeah, we're really excited to play a small part in this. Most of our work is in cement and concrete, but we do dabble in plastic. So yeah, really excited. Thanks.
Thank you. And all of our finalists are going to wear these around their neck for the rest of the night after they present. The cool Flava Flav style medallions to show that they are finalists for the Carbon Removal Challenge. And with that, I'm going to turn it back over to the MC, Chris Neidl.
Great, thank you, Matt. Big round of applause. If you only knew how much work went into this with a very small and dedicated staff, it's really inspiring. And as Matt's co-founder of OpenAir, I was kind of tuned out to this last year because I was busy working on other stuff, and I tuned into the stream for it, and it just blew my mind that groups of students were coming up with such a creative and nearly commercial ideas. So I'm extremely excited to hear from the teams tonight. We have 5 teams that were selected as finalists. Each will give 8-minute presentations, and each was also, in addition to being selected as a finalist, was designated as under particular superlative categories, so things that their projects really stood out for. So I'd like to announce the first team. I'll tell you a little bit about the superlative, and they'll come up and they'll tell you about their project. So the first team that is joining us is coming from Okinawa, Japan, the Okinawa Institute of Science and Technology, and their project is called Eternal Air, and the team members will come and introduce themselves and tell you a bit about their project. Come on up, guys.
Hello everyone. I'm Jolan from the Eternal Air team. This is Josephine and this is Jonas. Can Can I get, okay, I got my slides up. Let me just make sure everything's working. Okay, so here is our team. It was created around 5 months ago, which is quite short, and we are all scientists from the Okinawan Institute of Science and Technology. Today, we are proud to present you Eternal Air, a prototype which in its current state can serve to test solid sorbents and, once incorporated into a waste heat recovery system, becomes a self-sufficient DAC system. Today, I will count you the story of how it came to be. Right, so we know we must remove the excess CO2 currently in our atmosphere. We've known this for a while, and there are plenty of DAC efforts out there. So the first question we asked ourselves was, how do DAC systems typically work? Well, in two phases. The adsorption phase, where the air comes into contact with a sorbent, which absorbs the CO2, and the desorption phase, where the sorbent is treated to release the CO2, which can then be stored away. As you can see, DAC systems' performance largely depend on their sorbent system. Now, according to the International Energy Agency, total DAC efforts only account for 0.01 megaton of CO2 per year. So the next question we asked ourselves was, why? Or in other words, what is hindering the efficiency of the sorbent systems? We regrouped the main issues here, and then we deduced that an ideal sorbent system not only needs a high CO2 intake, but also needs to display a low-energy desorption phase, be selective, cheap, simple, and robust. And based on these criteria, we chose a polyethylene imine-coated ceramic lattice as our sorbent system. The PEI captures the CO2, and the lattice simply serves as a heat-resistant solid support. As you can see, our sorbent system, and even more in comparison with a MOF, is extremely cost-effective. Okay, so how do we coat the lattice? Simply place it in a solution of water, PEI, and silica for 12 hours, which will look like this, and then remove it and dry it. No energy-intensive steps, no toxic chemicals, and the solution can actually be reused to drive down costs. Green and simple. Okay, so now if we look back at the criteria which I previously enumerated, our sorbent system ticks all of the boxes, at least in theory. So we had to come up with a proof of concept experiment where we joined 3 plastic boxes together with some PVC pipes, added a CO2 sensor in the first box, the sorbent system in the second box, and a CO2 sensor in the third box. We blew air into the system, heated it, and recorded CO2 levels. Based on our results, we can confidently say that our system indeed releases CO2 upon heating. Okay, so we now have a very basic temperature swing DAC system, but if we want to remove gigatons of CO2, we need more than that. We need a system which captures CO2 without emitting any. Okay, so in our system, we have 2 main heat-emitting sources, our heat source and our vacuum pump. Both of them will be removed by incorporating Eternal Air into a waste heat recovery unit. Our heat source will be replaced by waste heat, low temperature waste heat, which is not only abundant, but available. So in order to measure the temperature, the minimum working temperature of our system, and thus establish which waste heat recovery system would be suitable for it, we built a new prototype, which is here represented. Its general mechanism is as follows. You blow air into the system, the sorbent captures CO2. Once it is saturated, the valves close, and we apply vacuum to remove the air. Heating then releases the CO2, which can then be stored away using vacuum. Okay, and the valves can now be reopened and the process repeated again. Our minimum temperature was measured around 65 degrees. Now, due to technical reasons, we perform this desorption at ambient pressure, and we can therefore guarantee that in our final system, this temperature will be lower. In other words, Eternal Air is suitable for basically any existing waste heat recovery units. We also tried to quantify the amount of CO2 that Eternal Air could capture, but we reached shortcomings when our system desorbed so much that we reached our CO2 sensor's upper limit, which is extremely promising. Nevertheless, while we were waiting for our CO2 sensors to arrive, an estimation of our CO2 uptake was calculated at 700 milligrams per gram. That would make it one of the best sorbent systems up to date. Now, this is unlikely, but it highlights something really important. The current scientific method to measure CO2 uptake is not necessarily always representative of the sorbent's performance in real DAC environments. What this does is it creates a gap between the scientists who create and study these sorbents and the entrepreneurs who wish to use them. For this reason, we would like to propose Eternal Air as a novel sorbent tester and invite anyone who is interested to come and talk to us. Okay, so now we've just shown that Eternal Air, we've just shown that we can remove the emission from the heat source using waste heat. Yet, we are yet to reach a self-sufficient system. In this regard, our vacuum pump will be replaced by a water aspirator, a very simple and cheap device which can, only using a water source, achieve vacuum. Since waste heat is generally transported as hot water in pipes, simply connecting this device to a pipe will remove the need for our pump. However, when we apply vacuum in this way, sorry for the other side, but the air from the system goes into the water. What that means is if we apply vacuum after the desorption of CO2, the CO2 will also go into the water. In order to avoid this, we need to play around with the valves, and therefore, this eventually means that we cannot capture all of the trapped CO2. So our system is less efficient, but now fully self-sufficient. Our next steps will be to perform experiments in order to test the performance of this system, obviously. Okay, so now Eternal Air can capture CO2 without emitting any. However, CO2 storage still remains an open question in this project, and any suggestion or collaboration for this matter will be open, or will be very welcome. Now, I'd like to finish on a very important feature of DAC system, scalability. Immediately, everyone thinks about making everything really big. In our case, heating up a huge metal box doesn't sound very efficient or practical for that matter. Rather, I would like you to think about the gigantic number of waste heat recovery units which exist throughout the world. With its customizable lattice and its low regeneration temperature, Eternal Air was designed to be able to adapt to each and every single one of them. With an estimated cost for a full-size, self-sufficient DAC system under the $500 benchmark, we believe that Eternal Air could very well decarbonate the world. Thank you very much.
Fantastic. Eternal Air, one more time, guys. Give it a round of applause, please. Great. Joining us all the way from Okinawa. And I should have mentioned that the award that the Eternal Air team received for this was highest quality report, which means it was the most comprehensive and well-prepared submission in terms of the data that they included in their proposal. So moving right along, we actually have another direct air capture project, this time from a team more local in Ontario, London, Ontario, Canada, at Western University. And, oh, I think I might have skipped. Yeah, here we go, great. And this project is the DAC device with novel sorbent geometry. So we'd like to invite that team come up and present their project.
Hello, we are the Green Technology Club from Western University, London, Ontario, Canada. We're here to talk today about our direct air carbon capture device with a novel sorbent geometry that is 3D printed. So to start off, just to meet the team, my name is Louis Klug. Up on stage with me today is Ethan, Eric, Kiara, Liam, and Sarah. So we started off with the problem statement, which is that there is a need to improve the efficiency of sorbent materials for a mechatronic device to efficiently capture greenhouse gas emissions. So our solution involves two components. One is a DAC device, and the other are the 3D printed sorbents. These two components come together to create a device with improved energy efficiency. So up on screen is a CAD representation of our device, as well as a picture of the final product, or at least a prototype. So I'm going to pass it off to Liam now to talk about the sorbent geometry.
Great, thanks, Louis. So as Louis mentioned, a big part of our project is this novel sorbent geometry that we created. With current solid sorbent DAC devices, a big issue is improving the efficiency of the fluid flow through these devices. So we basically simplified this problem down to creating a device or a structure that maximized surface area, assuming that increased surface area meant greater absorption of CO2, as well as lowering the pressure drop across our device, because lowering this pressure drop means that less energy needs to go into the fan to blow air through our device. So overall, increasing the efficiency. As you can see in the image here, this is the final design we came up with. We use zeolite as our active material, as well as methylcellulose, bentonite clay, polyvinyl alcohol, and water in different concentrations to come up with a sort of viscous material that was printable, had a high amount of active zeolite, and also provided the structural integrity that we needed for these structures. So if we could get next slide. Thanks. So how did we get here? We looked at different manufacturing techniques. In the end, we went with 3D printing. So we used an Ender 3D printer, modified it for our viscous material. And then we looked at printing different shapes. So we looked at things such as TPMS, or triply periodic minimal surfaces, which are known to have very high surface areas, as well as rectangular lattices. And as you can see in the image on the far right, we did have some issues with 3D printing. These structures were not easy to print. In the future, we want to work on this and try to print these shapes, but that's why we went with that sort of wavy line design in the end. So now I'll pass it off to Sarah.
Thanks, Liam. So our first result was that we included a user display to allow the user to initiate processes and also to see what was happening inside the chamber. Our first result that we got was in the adsorption stage. So we placed CO2 sensors on the inlet and outlet airflow. As you can see in the graph, the outlet airflow had a good decrease in CO2 levels compared to the inlet, and this really showed the effectiveness of our sorbent in capturing CO2. The next thing was we needed to heat up the sorbent to 120 degrees Celsius to ensure that the sorbent could let go of all the CO2. We placed temperature sensors around the perimeter and the center of the sorbent, and as shown in the graph, we were able to achieve the temperature needed. And now I'll pass it off to Eric to talk about desorption.
Yeah, so desorption is where it heats up and we actually start collecting the CO2. So the sorbent starts releasing it, and we have a output flow sensor that will start to measure the concentration and total mass we can capture. And in terms of numbers, our cycle is about 20 to 30 minutes long, captures about around 10 grams of carbon and uses 40.5 watt hours of energy. So this comes to a total efficiency of 251.52 grams per kilowatt hour, or to compare to other DAC devices, a better metric would be around 4,000 kilowatt hours per ton. And Kira will talk about our next steps in the project.
Thanks, Eric. So in terms of next steps, our team has really narrowed it down to around 4 main improvements. So starting with the device itself, how we designed it was that we have 2 chambers, and as one heats up, the other one cools down, and then it cycles through. So what we want to do in the future is we want to be able to use that waste heat from the one that's cooling down to be able to then heat up the other one using a heat exchanger. Second, we want to research capture kinetics. As was previously mentioned, we did originally assume that increasing that surface area and decreasing that pressure drop will automatically create a better sorbent. However, we want to be able to see if we can maybe decrease that surface area from what we originally have and keeping the same pressure drop to be able to get the same material properties, or rather even better material properties to be able to capture carbon. And third, the next one was the Ender that we modified in terms of the printer itself. What we did is that we had a couple of modifications that we wanted to do and that we actually did end up doing. But what we want to be able to do is actually increase the robustness of the sorbent that we did. So to do this, we want to be able to increase the reliability along with decreasing that printing time, just to make it a bit more feasible in terms of a longer scale impact. And then finally, the test that we did complete actually only contained a half-filled sorbent. So we want to be able to take that next step and get even more accurate results with our full-scale version of the prototype. And I'll pass it off to Ethan to talk about our vision.
Thanks, Kira. So I'm sure what all of you are here to about is how are we going to save the world? And this is our vision for the project. Our thunder was stolen a little bit by the previous team, but imagine if every single home in the world had one of these devices on it. A lot of the DAC devices you see today are large-scale installations that take up kilometers of space. If we could put this device on every single home, while it might only be capturing a little bit of CO2 per device, it could have a huge impact across the world. Just looking at some math here, our device would capture about 107 kilograms of CO2 per device per year. Now imagine every home in America had this device. That's 144 million homes and 15.42 million tons captured per year. This is with our initial results only capturing 10 grams of CO2 per cycle. Obviously, if we improve our efficiency and improve the performance of device, this capture amount would greatly improve. Again, also only across America. There is, of course, some challenges to this problem and achieving this scale, the first being efficient printing. As both Liam and Kira mentioned earlier, these prints take about 10 to 15 hours to complete. So printing all of these at once would be a huge challenge, especially if you wanted to put them, again, across the entire world. Again, mass production is also a major challenge for this project. We'd have to scale up the ability to produce one device for every single person, and demand is also important. While these large companies are producing massive DAC devices, the demand is mostly on these companies to produce them, whereas if we're selling this to an individual, we need to convince every single person in the United States or the world to purchase one of these devices, and that would be a huge roadblock for our project. Thank you for listening. If you have any questions, you can find us outside.
Thank you. Great. Thank you so much, team. That was excellent. And I should mention that the team that is exiting the stage right now, the superlative award that they won was Best Researched Project. So just assessing, as I think was reflected well in the presentation. So moving on to team number 3, it's the Monash Carbon Capture and Conversion Project. And this team is actually supported by 2 different schools in partnership, Trent University and Melbourne University, or in Melbourne, Australia, and the University of Ottawa.
No, just University of Melbourne.
Oh, okay, sorry, I see that there's two things here, okay. 2 Ottawas, I guess.
University of Melbourne.
The University of Melbourne?
University of Monash.
University of Monash. Okay, gotcha. A little bit of a typo here. It's right in the name. And this team, who you'll hear from right now, they actually, the superlative award that they received was Best Knowledge Gap Filler. And this refers actually to a report that's been produced by Frontier Carbon that was looking at where are the real big gaps that we fundamentally have in our knowledge in order to really scale up different forms of carbon removal. And so this project was judged to actually be the most sort of aligned with that report and potentially the biggest knowledge gap filler. So with that, I want to welcome the team to the stage. Thanks, guys.
Cool. So good afternoon, everyone. Firstly, I just want to start by saying it's a massive honor for us to be able to present here at Carbon Unbound. So thanks to Matt, Owen, the OpenAir team, and of course the sponsors for giving us the opportunity. So yeah, by way of introduction, my name's Jaden. This is Jack, Will, and Charlotte, and we're part of the Monash Carbon Capture and Conversion student team, which is a volunteer group at Monash University in Melbourne, Australia. And so we're united by a common passion for carbon removal, and so in doing that we've worked on developing an end-to-end solution which captures atmospheric carbon dioxide and converts it into, I guess, a useful and commercial product in ethylene. Cool. So as I just mentioned, our proposed solution is end-to-end. So carbon dioxide from the atmosphere converted to a useful product, that's ethylene. This can be done in 3 steps. So the first one is a direct air capture or an absorption step. And this was principally looked into by Jack and myself. And in doing so, we've developed 2, I guess, small prototypes to facilitate the CO2 absorption into our liquid absorbent. So coming out of the absorber, you have an absorbent that's rich in bound CO2. And Will's been principally looking into utilizing electrochemically mediated amine regeneration, or EMAR, to reduce the energy requirement of this CO2 liberation step. And thirdly is the utilization step. So Charlotte's been looking into the viability of converting the captured CO2 gas into ethylene. Cool.
Cool. I'll start off by talking about a key part of DAC systems, which is the choice of sorbent. This is important specifically for liquid DAC because solvent regeneration and desorption contributes the most to the overall energy requirement. And as we can see in this graph, the first three that we've got there are thermal pathways of desorbing sorbents, and those are far higher than what we see for EMA desorption using MEA or alkylamines. However, we know that for MEAs, they are quite volatile and harmful to the environment. And that's why we decided to look at amino acid salts as an alternative to this, as they are cheaper, non-toxic, and non-volatile. And as there is limited research on this, that's the knowledge gap that we targeted for this project.
Yeah, so to facilitate, I guess, looking into the absorption step, our first point of call was to develop a counterflow contactor, which I guess is similar in working principle to an absorption column, if anyone knows what that is, where air or gas comes in from the bottom and contacts with the liquid absorbent over the packing material. So this prototype, which is pictured to the right, essentially works to absorb the CO2, and we have a CO2 sensor connected through the outlet gas line to monitor the efficiency of the system in real time. So for baseline performance testing of this system, we cycled 0.5 mole of glycine through the contactor, and that gave a outlet concentration profile as up on the screen, which is compared to a pure water baseline. And doing some numerical integration, we determined that the system efficiency was around 0.3 kilowatt hours per mole of CO2, which I guess is a bit abstract, but it's comparing it to reported values in the literature for large-scale contactors, it's quite bad, of course, as you'd expect. So Carbon Engineering report an efficiency of their contactor, which is around 2 orders of magnitude better than that. So we obviously have a long way to go, but yeah.
Cool. Leading on from that, building on our first contactor, we developed a second one, utilizing crossflow, where the liquid and air contact perpendicularly. And we chose this for its high performance potential, specifically for the flow rates we can get, which are high for both liquid and air. And for this prototype, we've developed a much larger scale contactor with a 30 centimeter cubed contacting area. And we've also tried to make all components modular to make rapid prototyping possible. And currently, we've started initial testing with a 3D printed honeycomb lattice structured packing. And we hope to develop other contactor geometries and hybrid packing materials.
All right. So sorry if this section gets a little technical, guys. If you didn't hear it before, my name's Will. I'm going to take you through section 2 and 3 of that block flow diagram there, specifically my research into EMR desorption. So if you don't know, EMR desorption is electrochemically mediated amine regeneration. It's where you use electrical energy to desorb CO2 from a CO2 saturated solution. Specifically, you do this by cycling copper ions through a cell. These copper ions work to displace CO2 from the sorbent molecules itself. Next slide. So obviously, this is a bit different to what we usually do when we do thermal desorption, right? In thermal desorption, you can get temperatures upwards of 1,000 degrees Fahrenheit, and obviously with this comes an energy cost and also a flexibility cost there. You can only have them in specific places where there is a lot of waste heat. This is the complete opposite with EMR desorption, which can be run at or just above ambient temperatures. Not only does this improve the energy efficiency, it also makes it much more flexible. This gives it niches within both the flue gas industry and also non-point source capture. Next slide. Yep, told you guys it'd get a bit technical. Essentially, what we have here is some preliminary data on monoethanolamine, which I've conducted, which is the most common flue gas scrubber in the world. Essentially, the only thing to pay attention to is A1 and B1, which represents our copper oxidation and reduction. You can also see a similarity in shape to literature, which we've seen there. Essentially, what this shows is that we have successfully cycled copper through our cell, which is one of the key mainstays of being able to desorb the CO2 from solution. Next slide. Yep. So then this, the research we did there is now informing our work into a Gen 1 prototype, specifically glycine and potassium glycinate. As you heard before, we're looking into it for its energy efficiency and its and its environmental safety. Yeah, essentially there you can see we're doing some preliminary work, and our proposed design here that the team is working on will hopefully desorb 10 to 15 grams of CO2 per day and use energy efficient modules such as an anion exchange membrane with a low voltage drop across it. Essentially all this is to produce a pure CO2 stream for the next part of our project, CO2 reduction.
Thanks, Will. So the final step in our end-to-end solution is the conversion of the captured carbon dioxide into ethylene to provide a usable product at the end. The reason that we chose ethylene is because it's a building block for so many crucial chemicals and end products that span across multiple industries. To begin our lab work, we started with a beaker cell to provide proof of concept for what we're doing. We ran some tests that showed some reduction, oxidation occurring. We haven't gone much further than that, but it's a promising first step to show that something's happening and we're working towards producing ethylene. Moving on to some future work, we need to construct a flow cell to facilitate the continuous reduction to ethylene. We currently have, this is our current prototype. It's quite small. It's about 5 centimeters by 5 centimeters. But the good thing about flow cells as well is that they can be linearly scaled up. And what we want to do next is create this one here that has all the relevant electrodes and membranes that work to make it selective for ethylene and make it actually work. So, yeah.
Cool. So just to wrap it up really quickly, obviously the work we've done, I guess, establishes the 3 components in isolation. And our vision, I suppose, for the next coming months is to, 1, scale up the individual components of our tech, and then to, I guess, integrate it into one end-to-end solution. Cool. Thank you.
All right, excellent. So we'll be moving along to our 4th of 5 teams. Joining us from Trent University and the University of Ottawa and Peterborough, Ontario in Canada. This project name is Limex, calcium oxide looping. And the superlative award that they received, which is exciting, is the most potential impact at scale. So with that, I'd like to welcome the team to the stage.
All right, we are Limex, and I'm super excited to tell you about calcium oxide looping because it is disruptive, and it is simple, and it is scalable. My name is Lance Dossi, and I am our Chief Executive Officer and CTO. Alongside me is our lead mechanical engineer, Alexandru Talea. And together, we're going to show you how we're going to change the world and tackle one of the most pressing problems to date. Can we make a technology that can scale to a meaningful scale to capture carbon dioxide from the air? We know 3 things are true. It needs to be, 1, made up of abundant materials. Number 2, it needs to be made from low costs and able to scale rapidly to buy down the cost of carbon removal to make a meaningful impact. And our project starts simple. On this map, we are on the red star, Canada to the north and United States to the south. If we keep zooming in, we actually outline part of Manhattan. And this is around 50 kilometers squared or 19 miles squared. And this is actually just the land that we need to capture 3% of the world's emissions. And so we're going to jump in why that is. Number 1. We use one of the most simple and inexpensive materials, limestone. This is majorly produced and allows us to use a material to rapidly scale. We are simple. We are putting powder on trays. This allows us to scale as quickly as possible using the exact same engineering at every single scale. And this vertical integration allows us to become the most land-efficient process to date. And we're going to jump into why that is. So it's simple. This process takes limestone, calcium carbonate powder. And what we first do is we put it in a calciner, which heats up the powder to 900 degrees and strips off the carbon dioxide, able in a pure stream to inject into cement or underground for permanent storage. And what we're left with is called calcium oxide powder. And when we expose this to water, it forms this mineral called calcium hydroxide. And when we expose it to the air, it captures atmospheric carbon dioxide very rapidly to reform calcium carbonate. We can do this loop almost infinitely amount of times with our powder, making us a super scalable and rapid CO2 capturing approach. And so we wanted to take it to the lab and understand what was happening. And one of our big results is that we found different ways to capture over 90% efficiency with our material by testing different humidities. We also tried a kilogram of materials at different thicknesses, and we found an ideal thickness of around 1.3 millimeters or 1/16-inch thickness of calcium hydroxide powder, as seen on the top right corner. Our third thing, which is incredible, that we can capture carbon dioxide 2 tons for every ton of calcium hydroxide every single day. And from this is our optimizations, but it wasn't so simple. We started by putting powder outside and seeing what would happen. On our starting material, this is a picture under by shooting in electrons. This is the image we get of calcium oxide. And when we put outside, we get this image on the right that only captures 40% carbon dioxide. So we actually had to do a lot better. And we found different ways and different experiments and took it back to the lab. We started with calcium oxide and we took it stepwise. Well, if we take calcium oxide, let it react with the water in the air to form pure calcium hydroxide, and then with the best humidity, capture carbon dioxide. And that led us to calcium carbonate over 90% efficiency. And this brings us to understanding one of the most critical factors in scaling this and leads us to our engineering to envision what the future will look like.
Now, with the science and the results out of the way, let's dive into how we engineered the system. So firstly, of course, we started with a few design constraints. We wanted to create a product that was efficient in land usage. We wanted to design something with a long-term design life and create an automated system to improve our efficiencies and productivity on our site, as well as obviously reducing the costs as much as possible. Now, we started off with the conceptual design, which meant coming up with mechanical subsystems that were optimized to automate the system. And so the first subsystem were swinging plates. These hold our material and swing it down into the next step of our process. We have vibrating posts. This vibrates our system and displaces the material to create the ideal thickness that we'd want. A calciner, of course, to heat our material and give off our 2 byproducts. Conveyor belts that will connect each tray system. And finally, a hydraulic sprinkler system installed on each tray that will hydrate our material. And so to visualize this a little better, let's look at our engineering looping process. We first start with our calcium carbonate stacked up onto our trays, followed by the swinging system where the material will fall into our calciner, heat it to 900 degrees, form our 2 byproducts of CO2, and our hydroxide, or calcium oxide, which is then hydrated with water. The vibrating posts also vibrate the system in order to get that desired thickness, and it's distributed back onto our tray system, which is then left out to react with atmospheric carbon dioxide.
And this approach is simple. We just stack powder on trays using the most inexpensive, simple, and abundant material known to man. And just to outline, this is Manhattan. We can capture 3% of the world's emissions today. This is critical, and this is only enabled by our focus on environmental issues that we all together can tackle. We're bringing down economics, making prosperity to everyone, and increasing social awareness, but also driving social change. And this sustainable approach is exciting, and why we're very thankful for our Trent University and Power Jew Lab for allowing us to do all this research, University of Ottawa for the engineering, and OpenAir Collective for putting on all of this and allowing us to come present to you one of these new ideas that are very exciting. And additionally, we'd love to connect with you and see how we can change the world together. But from our work, what was done is we just published our first paper in the Journal of Cleaner Production. This is open access. Anyone can read it, and you can learn about calcium oxide looping, how it works, and how it really is going to change the world. So thank you very much for everyone for coming to our presentation today. Thank you.
Excellent. Fantastic. That was fascinating. All right, so we're now up to our fifth and final team, which I'd like to welcome to the stage right now, which is really exciting. So Waterloo DAC system with algae integrated removal. Definitely sounds interesting. And from its title, you might guess its superlative award was Most Novel Approach, which I certainly like those. So this team represents the University of Waterloo, based in Waterloo, Canada. And with that, I'd like to welcome this team to the stage.
Hello, everyone. We are a team of engineering undergraduate students from the University of Waterloo in Canada. We have created the Waterloo prototype as seen on the screen. It is a closed-loop solution that captures carbon directly from the air and produces an algae value-add product. Before we delve too far into the design, we would like to thank the OpenAir Collective and Carbon Unbound for hosting us and providing us the opportunity to be here. All right, let's meet the team. My name is Anjia Sharif, and I am joined by Robert Duff, Sophia Kaleka, Hussein Hassan Ali, and our project advisor is Dr. Wu, professor in mechanical engineering. We have created 3 iterations of DAC devices over the past 3 years, and we have done this in collaboration with Engineers Without Borders on campus, through which we've had the help of 15 undergraduate students, majority in chemical and environmental engineering. So here is the underlying principle of our device. We have the capture reactor and we have the utilization reactor. How the capture works is air is put in through the bottom of the reactor and the sorbent is fluidized. And this fluidization selectively captures the CO2. This is the capture stage. To release the CO2, we add water from the top of the reactor, and this transfers the CO2 into the water phase, and this effectively releases the CO2 and creates a carbonated water end product. With this carbonated water end product, we feed it into an algae reactor along with nutrients to create a vitamin-rich algae product, which is very efficient as a food supplement, as well as in the cosmetic industries. Here is an overview of what we've built. The key things to note on this diagram is item C, which is our capture reactor, and item H, which is our algae reactor. All other components are supporting material transport and automation of the entire system. Here is the device in action. So this is the capture stage. The air is blowing in. It is fluidizing our sorbent and allowing for capture. It's pulsed to avoid overheating the blower. And our airspeed is approximately 2.5 meters per second. Here is the release stage. It begins with the water being misted down from the top. The sorbent is submerged and the CO2 is transferred into the water phase. Here is the utilization in action. First, the matured algae gets moved out of the system just to prevent dilution of the mixture and also to prevent overflowing. Once this is complete, we have this carbonated water and the nutrients fed in to redo the cycle and create more algae.
Thanks. So now that you've seen how the device works, we just wanted to walk you through some of our design process, first starting with the capture side. and why we went with moisture swing in the first place compared to thermal swing or any other method. So relatively, the sorbent for moisture swing is more low cost, and in particular, the drying, which is required for regeneration of the sorbent, is much less energy intensive, and this makes it more suitable for open source applications. In addition, in terms of the design itself, we're looking at using the fluidized bed so that we can get the maximum surface area from the sorbent rather than having it on a filter or some other kind of geometry, just so the entire beads can be exposed. And we also followed a novel pre-treatment process for the sorbent to increase its affinity for CO2. In terms of the utilization side with the microalgae, we think it has a lot of promise because it has low environmental CO2 leakage compared to other methods. It's low power requirement to maintain, and it uses cheap nutrient feedstocks to grow and doesn't require any arable land. And so it's a useful and sellable byproduct. Compared to other terrestrial plants, it has a higher CO2 conversion rate. But this is where one of the cons actually comes from, is that to unlock this higher rate, you really need to grow it in some sort of controlled environment in a bioreactor. And of course, there's a significant cost and complexity to do this.
Now, in order to accurately determine how much carbon dioxide the system would be able to offset during its operation, we found it a critical step to perform a full carbon life cycle analysis. So upon analysis of our electrical components, we determined that the energy consumption of the device was approximately less than half of a kilowatt hour for every one carbon capture cycle. We also performed tests on each of the electrical components, as well as emissions data from the Ontario power grid on which the system would be operating to determine that the approximate footprint of the system was around 14.4 grams of CO2 for every one capture cycle. The figures on the right will break down the exact footprint of each cycle, the dry condition from when the carbon is captured, the humid condition when that CO2 is then utilized in the water, and then the algae growth stage where that water is used to grow the algae. Ultimately, next one. Thank you. We also found that it was important to look at the footprint of the materials used in the process as well. So those accounted for around 130 grams of carbon dioxide. Ultimately, these emissions are not a direct result of our system's operation. However, our goal is to use all of the carbon footprint data to compare with the amount of carbon captured by the system to determine accurately how much it will be able to offset. Our current system for MRV at this point was not able to verify how much exactly the carbon dioxide it would be able to capture, but we do have an active plan in place to improve the MRV of the system, which will be discussed further.
Awesome. So one of the steps, our first step for MRV is how do we quantify the CO2 captured by a system? So based off a non-dispersive infrared or NDIR CO2 sensing platform, our system measures and plots the CO2 concentration in the outlet air from our reactor or our column to allow for breakthrough analysis, which is a key aspect of determining the adsorptive capacity of materials under flow conditions. A limitation of this platform is that since CO2 and water vapor in air have similar light absorbance, the NDIR sensor has difficulty differentiating between the two. This is characterized through the enclosed red boxes where a peak in humidity corresponds to a peak in CO2 concentration. As a secondary step for MRV, we performed algal growth tests using the bioreactor company's mini bioreactor platform. In these tests, we compared the growth using the system waters to growth using bottled water, which has known properties. Although the growth was not exponential, like with the bottled water, the algae grown using our system process waters did show a change in optical density from 1.65 to 1.8, which demonstrates that some carbon dioxide was captured and contained in our process waters. For future improvement, we're focusing on three main areas, the first being improved sensors. In collaboration with the bioreactor company, we are developing a dissolved CO2 system for mini bioreactors. This will allow us to directly calculate the dissolved CO2 in our process to improve that reporting section. We'll also be developing a low-cost, small-scale gas chromatograph for inline measurement of CO2 to combat the NDIR sensor issue. Our next step is improving the capture efficiency. We'll be trialing different sorbents, such as activated carbon, as well as different drying methods, and evaluating the applicability of mechanical stress to improve the drying cycle of the system.
And lastly, to improve the overall circularity of the system, we are looking at a partnership with the Waterloo Center for Microbial Research. This is a research lab on campus that is focused on utilizing wastewater of various sources to help grow algae. The figure on the left will show you an example of the algae species that we're using growing in wastewater, so this is very possible. As well, we're looking at the implementation of an airlift photobioreactor design, which will help ultimately improve the algal yields so we can have more useful biomass production. And with that, we would like to thank you all very much for your time this evening to learn about our presentation, and we're looking forward to the coming days. Thank you.
Thank you so much.
Excellent. Fantastic. Well, that was our final team, and that brings to a conclusion our program for tonight. But I do want to just say that when me and Matt started OpenAir about 6 years ago, the premise was, could you create a community of people who cared about climate and carbon removal and would be willing to join and contribute as teams, as volunteers to do amazing things. And in the years since, we've had many different projects. We have a lot of OpenAir members here who have passed legislation in states and people who have started novel business models and made really, really cool things. But I have to say, I think that the Carbon Removal Challenge, now in its second year, I think is just an example of you put a call out to the world and you can get amazing things from all corners on the way back. In some ways, it's the most inspiring and clear articulation of the OpenAir idea. So I really want to thank all the teams, and please join me with a round of applause. Please stand up, guys, if you can. Please stand up. Excellent. Really impressive. And I also want to say, I'm sure Matt will take a couple of days off with Duncan and Owen, who made big contributions, but this is our second, and we definitely plan to have a third, fourth, and fifth, and to get bigger and better each time. And so we are, certainly we can talk to you for drinks right now if folks are interested in being a partner for next year's session. We have much to tell you and to share. And again, I would like to thank all of our sponsors. Really, really deep appreciation for the Reinhardts, our sponsors, and for Carbon Unbound. And right now we will have drinks. I'm not sure if we have our drink sponsor here. Emily is here, maybe our most important speaker of the night. I'm not sure. Over here, who's going to tell you a little bit about where she's coming from. But join us for drinks, and let's continue the discussion. Thanks, Emily.